I do actually. Can
Okay.
you go over question 107 from chapter 4?
107, that's the 3 blocks with the tension in each one. So this is chapter 4, problem 107. So we can assume they all have the same acceleration. I forget, the masses are all the same and they're all tied to the string being pulled. I think that sums it up. Let me check the wording just to see how generically I'm gonna talk. Identical blocks are pulled as shown on the horizontal frictional surface. If the tension in the rope held by the hand is 30 newtons, discuss what is the tension in the other ropes. So this is 30 newtons right here. So what is the tension here? And what is the tension here? I'm gonna call that FT1 and FT2. Now, they don't tell us what the mass of the 3 are. And I just read it. That identical. They are identical. So I can make up a mass. There's absolutely no problem with that as long as I don't violate anything. They're identical, so as long as my masses are all the same, I'm still good. So I'm just gonna make this, we'll just make it 1 kilogram, 1 kilogram, and 1 kilogram. So what is the total mass that's being accelerated?
3 kilograms,
What is the force that I'm applying?
30 newtons.
So if I look at Newton's second law, F equals ma, the total force I'm applying is 30 newtons, is equal to my mass, which is 3 kilograms, times acceleration. So the math problem is 30 is equal to 3a, that's the math problem. What is the acceleration?
10
Do the whole thing.
meters per second squared.
There we go. So acceleration is 10 meters per second squared. So that has to be the acceleration of all 3 of them. So let's take a look at it at a different level. Let's take a look at just this one. This one is being pulled by this rope. Doesn't care about any of that stuff. This is being pulled by this one rope right here. This is the thing that exerts force. This 30 Newton force is applied to this mass, but all 3 are being accelerated by it. But if I look at just that one mass right there, I have my 1 kilogram mass right there, and I have a tension pulling on it. What is its acceleration?
Meters per second squared.
Right. We've already established they're all accelerating the same. They're all accelerating at 10 meters per second squared. I know the mass here, so my tension 1 has to be the mass of this, 1 kilogram, times the acceleration. Doing the fancy math here, we get 10 newtons. So the tension in this one is 10 newtons. So I've got I'm gonna call this A, B, and C. So if I did a full force diagram, I've got mass A, I got a rope, I got mass B, I have a rope. I am running out of room here. You know what, this is just gonna go back up again here. A, B, C. Technically, there's a rope there too. So I have already established 30 newtons pulling here. I have 10 newtons pulling here. That's what we've done the calculations for already. it's the rope pulling this to the right, therefore this must be pulling the rope to the left. There must be a 10 newtons going back in that direction. We assume an ideal rope, so the tension is the magnitude of the tension is the same on this side, which means this is being pulled back with 10 newtons. Over here, I'm pulling on this with 30 newtons, which means that the tension on this side is 30 newtons, which means that's 30 newtons. And so now I have this last mystery force here. What is the tension on this rope right here? Well, I don't know, so I'm just gonna call it FT2. I know that total force is equal to mass times acceleration, or there are a lot of physicists that are gonna be angry if that's not true. FT2 minus 10 is equal to the mass of this times the acceleration. This is F equals ma. FT2 minus 10 equals 10. Tension 2 is equal to 20. So it's 10 newtons in the first rope, 20 newtons in the second rope, and the third rope has 30 newtons. We could have also looked at this rope between B and C slightly differently. I could have looked at this combined object here, being pulled by this rope, and done similar to what I did right here, the total mass being moved. What is the total mass that's being moved if I'm looking at just this?
2 kilograms.
My acceleration, still 10. So the tension that's pulling this whole thing is 20. There are several ways of looking at it. Try to present both ways, or two of them. Is that sufficient, Chancy, or?
Yes.
Okay.
Yeah, got it.
So you said you're using your own number in that, in those blocks?
Yes.
Any number can still come out the same?
Yes.
Okay.
What would change if I made these 10 kilograms each? Then my acceleration would have been 1. And so this would have been 10 kilograms times 1, which still gets me 10. Or if it would end up where you'd get the same answer for the tensions, no matter what. It's a convenient thing. There was I'm seeing this standardized test that my daughter took once, and she knew ahead of time she was gonna do it, and there were a couple of algebra problems in there, and I said, as long as you don't violate anything that they've said, just make up numbers and work it that way. It's a multiple choice test. Worst case scenario, you pick numbers and you eliminated all but 2 of them. Then you pick different numbers. All right, any other questions on this or another problem from 4 or 5? Any questions in relation to the test?
This is next month, right?
Yeah, it's the 5th.
And we have a quiz for 4 and 5 next week.
Yes.
And looking at old test and the homework that you assigned us for is something that we should be going over.
The homework from the textbook, definitely going over for that, but the quiz, the test, looking at old tests, I think is better than looking at the old homework problems, but I think the homework problems set up a foundation for this.
Just showing, we always not looking at it. All right.
And there's also master set questions that at some point I'll post solutions for. But the master set, I'm not requiring you to do but they're based on multiple test problems. At least through chapter 5. All right, so let's start on the first material for that is not on the test. And let's just go ahead.